In this video, we're going to work example problems related to the trigonometric or polar form of complex numbers. Now, try not to overcomplicate this. It sounds really scary, the trigonometric form of complex numbers. But remember, all we're talking about here is that, so we know that all numbers that currently exist in mathematics are contained within a plane. At least you can describe it that way. Like we can describe all real numbers as like being along a line. Well, we can describe all numbers that exist in mathematics, so all complex numbers which contain real numbers, as existing in a plane called the complex plane. And it's a plane instead of a line because it's two-dimensional because of the nature of how you can't, if you have something like 5 minus 3i, we can't combine this anymore. These are two distinctly separate parameters. So they go in their own distinct direction. So it's like two-dimensional, okay? But what you want to think about, though, is that when you think about the complex plane, so this plane, it extends infinitely in all directions, okay? You don't have to, this plane here contains all complex numbers, all the infinite complex numbers. But there's no like coordinate system that's married to this plane. The coordinate system is something that we come in and add just to aid in identifying different numbers in the plane. The complex plane itself looks like this, with there's numbers, infinite numbers everywhere. There's no coordinate system on it. We add the coordinate system, okay? And so the standard coordinate system that's used is, so the origin is always going to be at the center of the plane for any coordinate system you use, but the standard coordinate system that we use is a rectangular coordinate system, where you've got the real axis is horizontal, the imaginary axis is vertical, and it's like a rectangular coordinate system. You think of x and y, so a complex number is going to be x plus y I. That's it. So x can be positive or negative, y can be positive or negative, so this covers all possible points in the complex plane. Okay, but all we're doing in this section is we're removing the Cartesian coordinate system, and we're thinking about, okay, what if we want to use a polar coordinate system instead? Right, so this is like 1, 2, 3, 4, 5, 6, like the major tick marks for radius, and then measured from the positive horizontal direction is theta, going from 0 to 360, or I mean, it could go past 360 or go in negative directions, but, and then this is r. Okay, so instead of using x and y, those two parameters, to specify the location of a point in the plane, or to specify a complex number, we can use two other parameters, r and theta, because with something that's two-dimensional, to specify all points in a plane, or like, let's say 3D space, you could come up with any coordinate system you want, but no matter what, it's going to take three parameters because it's three-dimensional. So, and so for a plane, it's going to take two parameters. And so we're thinking about what would be the form that you would use to represent a point in a plane, but in that case, we're talking about the complex plane, so a complex number in polar coordinates instead of rectangular coordinates. That's it. It's just a matter of a coordinate system. Now, one thing to note, though, is that, yes, the forms are different, but we're referring to the exact same number. And so whether we represent this, no matter what form we represent this with coordinate system, we're still talking about the same number. So these numbers are equal in both of their forms. And so that's what we're going to see when we write out the polar form. If we simplify it, we get the exact same number that we have in rectangular form. So it's the exact same number. Like, there's no difference. It's just a different path of how you represent the number. It's the exact same number, though. It's really important for you to understand that, and it's going to be really illustrated here as we work these example problems. So, okay, For each complex number shown, give its rectangular form and its trigonometric or polar form. So we call this trigonometric because we need trig functions for the polar form. Okay, so, but we're going to have r be greater than 0 and the theta be between 0 and 360. You can have theta can be bigger than 360. Like, I mean, that's, you can put theta bigger than 360 into trig functions or negative thetas, but with this domain here, if you just restricted r to be greater than 0 and theta to be between 0 and 360, that represents all complex. You can represent everything in the plane that way. So, okay. So this number here, we've got, let's see, in rectangular form, this would be, it's just 2. I mean, okay, but 2 plus 0i, right? But it's a pure real number, so just 2. Okay. Now, okay, we're going to do this in the polar form, but once we simplify the polar form, we're going to get the exact same number. That's really important to realize. This is the exact same number. We're thinking about the complex plane here. We're just identifying numbers. It doesn't matter what coordinate system we use. We're identifying the same number, right? So no matter what form you use, once you simplify that form, they should come out to be the exact same, and they will. So, okay, B, we've got, let's see, so we know it's so like the rectangular form is x plus yi, the polar form is r cosine theta plus I sine theta. So here, r is 2 and theta is 0. So cosine 0 degrees plus I sine of 0 degrees. Sine of 0 is 0. Cosine of 0 is 1. So 2. There you go. Same number. Okay, here we've got, let's see, this is going to be like 0 plus 2i, right? Or just 2i. It's pure imaginary. 2i. Okay, so now in polar, we've got the radius is 2 and the theta is 90 this time, plus I sine of 90. Well, okay, sine of 90 is, so like this is, the number is 2i. The complex number is 2i. Here, okay, but it's the same number. The two z's are the same. I'm not saying z1 and z2. No, these are both the same z, same complex number. So z is, cosine 90 is 0, sine of 90 is 1, so 2i. Okay, so here we've got, let's see, z is equal to 2 plus 2i. Okay, now in polar, so this is going to be r and this is going to be theta. So r is just, you use the Pythagorean theorem, so 2 squared is 4 plus 2 squared. So we've got, so r is equal to 2 root 2. Okay, now we use the fact that tangent theta is going to be equal to 2 over 2 is going to be equal to 1. Now we're in the first quadrant, so we just do arc tangent of 1. So we know the 45, 45, 90 triangle, 1, 1, root 2. Tangent of 45 is 1. So, okay. Z is equal to, so we've got r is 2 root 2, and then we've got, so cosine of 45 plus I sine of 45. Okay, now we see cosine of 45 is going to be 1 over root 2, and so that's also going to be sine of 45. So now we distribute, and what do we get? 2 plus 2i, same number. Okay, for these problems, we're given a complex number in polar form, and we want to write it in rectangular form. So, again, you can think of this like, here's a complex number, z. And we just want to convert it from the polar form to the rectangular form. So all we need to do here is just simplify everything, because we can see that r is equal to 2. and theta is equal to 45 degrees. And so if we just distribute the two, we're going to have r cosine theta plus r sine theta, and that's what x and y are equal to. X is r cosine theta, y is r sine theta. So, all right, if we draw the reference 45, 45, 90 triangle, so cosine 45 is 1 over root 2. And sine of 45 is also 1 over root 2. Okay, so distributing the 2. Now rationalizing, so root 2 over root 2 times each of these results in, let's see, so 2 root 2 over 2 is just going to be root 2. So root 2 plus I root 2. And there we go. Okay, let's just distribute the 10 here. So cosine of 90 is 0, so we're left with 10i sine of 90. Sine of 90 is 1, so this is just 10i in rectangular form. Okay, 240 degrees is in the third quadrant with reference angle 60 degrees. Okay, if we think about the 30, 60, 90 triangle, 1 root 3 and 2. So this is going to be 2. This is going to be minus 1. This is going to be minus root 3. Okay, and that's 240 degrees. So, okay, cosine of 240 is going to be minus 1/2. So 4 plus I sine of 240, so minus root 3 over 2. So let's see. Okay, so minus 2 like that. So we can write it this way. There we go. We went from the polar form, we have the same complex number in rectangular form. Okay, this cis 150 is just the cosine plus I sine. That's how you think about this. This is equal to 3 times cosine of 150 plus I sine of 150. Okay, 150 is in the second quadrant with reference angle 30 degrees. Okay, so the 30, 60, 90 triangle will have 1, that's positive 1. This will be minus root 3, and so there's 150 degrees. So, okay, we've got Z is equal to so cosine of 150 is going to be minus root 3 over 2. Sine of 150 is going to be one over 2. So, okay, so we've got, let's see, minus 3 root 3 over 2 plus 1/2 I. Okay, so this complex number we know is 5 times cosine of 300 plus I sine of 300 degrees. Okay, 300 degrees is in the third quadrant with reference angle 60 degrees. So this is 30 degrees. We've got, this is going to be 1. This is going to be minus root 3, 2. Okay, so z is equal to, let's see. So this is 300. So cosine of 300 is going to be 1/2. And then sine 300, so minus root 3 over 2i. Okay, so 5/2 minus, there we go. Okay, so this complex number, we've got root 2 times cosine of 225 plus I sine of 225. So 225 is in the third quadrant with reference angle 45 degrees. Okay, so let's see, that's going to be minus 1 root 2. So, okay, we've got, so cosine 225 minus 1 over root 2, sine 225. Okay, so root 2 times minus 1 over root 2, that's minus 1, and then minus I. There we go. Okay. We just going to distribute this. So, okay, cosine of minus 30. So minus 30 is obviously in the fourth quadrant with reference angle 30 degrees. So let's see, we've got minus 1. Okay, so we've got 4 times, so cosine of minus 30 is root 3 over 2, and then sine of minus 30 is going to be minus 1 over 2. So we've got, let's see, we're going to have 2 root 3 minus 2i. There we go. Okay, so now here we're given a complex number in rectangular form, and we want to write it in polar form. So this doesn't work out to where we can just simplify it like we do the polar form and go straight into the rectangular form. But it's still not that big of a deal. So, okay, we've got minus 3, and so we can, and we can write this so we can clearly see the, let's do this, clearly see the imaginary part. Okay, and so we know that the rectangular form is x plus yi, right? But to go to polar form, all we're doing is, you know, you've got a point in the xy plane, which is like the complex plane, which you can think about. If we look at the rectangular form of a complex number like this, so you have x and y, but this is the complex plane. Well, any point anywhere, let's say over here, you can think about, you know, we're trying, this is a complex number, some complex number z. Okay, and it has coordinates x, y, where x could be negative, y could be negative. Okay, but we want to convert this to the r theta. Okay, well, we know r using the Pythagorean theorem, square root of x squared plus y squared. Okay, and then we have the relation that tangent theta is equal to y over x. Now, we're going to need to, because the arc tangent, so what this tells us is that we have theta is equal to arc tangent y over x, but we know the arc tangent goes from minus pi over 2 to pi over 2, the output. So we're just going to need to do a little bit of extra analysis to get the correct theta value, but it's not a big deal. Because, okay, so we can go ahead and do theta real quick. But let's go ahead and do theta first. So we see that for this complex number, the x is minus 3 and the y is minus 3 root 3. So we see we're in the fourth quadrant. And so that's really all we need to know. So now we can plug this into, so okay, y over x is going to be just root 3. So arc tangent of root 3 is going to or no, we're in the third quadrant. Yeah, third quadrant. So okay, but it gives us an angle in the first quadrant here because we know arc tangent is just going to output something in the first or fourth quadrant. But we know what this means in this case, since we can see we're in the third quadrant. That means we're going to have an angle in the third quadrant with reference angle 60. So 180 plus 60 is 240. So we know the angle is 240. Now we could use, like, what would this be, negative 120 or something, or we could use an angle greater than 360. That would still be valid, right? Because the math would still work out, but they want us to specify the angle between 0 and 360. Okay, so, all right, well, that's theta. Then r is going to be, let's see, so minus 3 squared is 9, and then minus 3 root 3 squared is going to be 9 times 3, so 27. So we've got, let's see. So r is equal to 6. Okay, and so now we have everything we need, so that the standard form for rectangular complex numbers is this, but the standard form for polar complex numbers is this. And so we just write it out. So we've got, let's see, 6 cosine of 240 plus I sine of 240. And that's it. And you might be wondering, well, how could we specify another angle, like an angle coterminal with 240? I mean, isn't the complex plane just one plane? Like, how can we specify some, like a different angle? Well, it's just if the math works out. The idea is, if we simplify this here, we're going to end up with this. Minus 3i root 3. And so if you specified, if instead of 240 you did, so 360 plus 240, 600 degrees. If you switched 240 with 600, it's going to be the same. You're going to have the same value here. So that's the idea. Mathematically, you still get the same value. So technically, any angle coterminal with 240 would work here. Okay, so let's see. We can see that x plus yi, so x is root 3, y is minus 1, so r is equal to, we've got 9 plus 1, so r is equal to root 10. Theta, we're going to have arc tangent of minus 1 over root 3. Okay, so let's go ahead and plug this in. Okay, so minus 30 degrees. But if we look here, so we see that we're actually going to be in quadrant 4. We actually are going to be in quadrant 4, positive x, negative y. So, and we're going to be in quadrant 4 with reference angle 30 degrees. So that's, we want to specify theta between 0 and 360. So the theta is going to be 330 degrees. And so there we go. Z in polar form is root 10 cosine of 330 plus I sine of 330. Okay, here we see we've got, let's see, x is minus 5, y is minus 5. So, okay, r is going to be 20, the square root of 25 plus 25. So, principal root of 50. We know that 50 is 25 times 2, so we've got 5 root 2. Okay, tangent theta, so y over x, so it's positive 1, so theta is arc tangent of positive 1, which we know that's going to be 45 degrees, okay, but what quadrant are we in here? Minus x minus y, we're in the third quadrant, so third quadrant with reference angle 45 is going to be 225. So there's r and theta, so we've got 5 root 2 cosine of 225 plus I sine 225. Okay, so we see x is equal to 2, y is equal to 2, so r is going to be the principal root of 8, so that's 4 times 2, so 2 root 2. Okay, theta, we've got arc tangent of 2 over 2, so is of 1, so it's 45 degrees, and we're in the first quadrant, so theta is going to be 45 degrees. So z is going to be 2 root 2 cosine of 45 degrees plus I sine of 45 degrees. Okay, there's the complex number. We see x is equal to 0, y is equal to 5, so r is just going to be 5, and theta is going to be, so okay, we're in the complex plane, we're here, so theta is 90. So we've got, let's see, z is 5 cosine 90 plus I sine 90. Okay, minus 4, that's still a complex number with x equal to minus 4 and y equal to 0, right, as far as the rectangular form of a complex number. So, okay, r is going to be equal to 4, positive 4, and then theta, we're over here, so theta is 180. So z is going to be equal to positive 4 cosine of 180 plus I sine of 180. Okay, the complex number z, where z is in rectangular form, can be graphed in the plane as x, y. Describe the graphs of all complex numbers z satisfying the given conditions. So the absolute value of z is 1. Okay, so we've got this complex number here in rectangular form with like, so here's an x value, here's a y value. So y, x. Okay, so the absolute value of z, that's the modulus, or the r value. So this is the absolute value of z. That's what they're talking about, this here. So all complex numbers that have absolute value 1. How can we describe that? Well, okay, that's going to be, so this is 1. That's all complex numbers on this circle here, the unit circle. Okay, what about with the real part of z being 1? Okay, so here's just the general complex plane with rectangular complex number here, z. So if the real part is 1, that's saying that we've got, we can look at it this way. That's like they're saying 1 plus yi. So what they're referring to here, you can think about is, so if we've got, okay, so that would be a vertical, this vertical line going through 1. All complex numbers on this vertical line here have real part equal to 1. So that's what this is referring to.